Okay, so as I said here in example 2, we're going to focus on condensing logarithmic expressions into a single logarithm. And so we're essentially just going backwards from what we just did. And so what you want to always do first is use the power rule to move any coefficients and make them exponents. And so for that first term, I'm going to have the natural log of x cubed minus the natural log of y to the 1/2 plus the natural log of z raised to the 5th. Just using the power rule to move all of these coefficients that are in front of the logarithm up to be the exponent on the argument. Now, from there, you're going to use the product and the quotient rule, and you can do this one step at a time if you want to, but it's probably easier just to use the following rule of thumb, if you will, for doing this. And here's the rule of thumb. Any logarithm that is positive will be sent to the numerator. So for example, this first logarithm is positive, and this logarithm here is positive. And so what that means is that when I write this as a single logarithm, those two expressions are going to go into the numerator. The only negative logarithm is this one in the middle, and any logarithm that's negative that's being subtracted is going to go into the denominator. And I'm going to go ahead and write that as the square root of y, and the reason I can do that is because it's raised to the 1/2 power, and that's just to reiterate that relationship between the 1/2 exponent and the concept of a square root. Now, letter B I've also put on this particular slide because it's very similar to letter A, but with one major difference. And the major difference is that now this is collected as a group inside of parentheses. And so what that means is that this entire thing is negative, which means that all of the expressions coming from this logarithm will have to go to the denominator once we get to that point. But once again, I'm going to start by backing up and erasing that 3 and using the power rule to write all of my coefficients as exponents. And so this is going to be minus natural log of y to the 1/2 plus the natural log of z to the 5th. And once again, as I said earlier, since both of those second two terms are in the parentheses with a minus sign, they are both going to the denominator. And so this will be natural log of x cubed and then divided by, I'm going to go ahead and write square root of y times z to the 5th power, with both of those things going in the denominator, whereas over here in example A, this plus 5 ln of z was not associated with the negative, and so that's why it wound up in the numerator here on letter A, but had to end up in the denominator on letter B. Okay, I'm just going to tell you up front that you're going to hate me for part C, and the reason is because of the final answer, and you'll understand what I mean when we get there. I have taught for long enough and have known enough students that the final answer is really going to make you mad here, so I'm just going to apologize up front, but hope that you'll stick with me and you'll be drawn in by my statement that you're going to be angry here in just a second. So let's go ahead and start this problem. We're going to begin by using the power rule and moving those coefficients to be exponents. And so this will say log base b of 27 to the 4/3 power minus log base b of 9 to the 2nd power. And so now we want to simplify if possible. And actually I'm going to keep going by using the quotient rule, and so this is going to be log base b of 27 to the 4/3 divided by 9 squared, which I know is 81. Okay, so why are you going to hate me? Well, here's why you're going to hate me. Because 27 to the 4/3, let's talk about that for just a second. You are going to need to be able to do that without a calculator. Now, does anyone here that's listening to this know what 27 to the 4th power is? Yeah, I didn't think so. Neither do I. I don't know what 27 to the 4th power is. And even if I did, there's no way I would know what the cube root of that number is. And so instead of doing it that way, we're going to do it this way. We're going to start with 27, but instead of going to the 4th power, we're going to first go to the 1/3 power. And remember, 1/3, that just means cube root. So what is the cube root of 27. Well, I know what that is. I know that that's 3. And then I'm going to raise that number to the 4th. And I know that 3 to the 4th is 81. Okay, so that actually works a lot of the time. So that could be like your example 1 for this little trick. Example 2 would be like, what if you had 9 to the 3 halves? Well, you probably don't know what 9 to the 3rd is. Even if you did, you probably don't know what the square root of that is. But do you know what 9 to the 1/2 is? Well, yeah, that's the square root of 9, which is 3. And then, do you know what 3 cubed is? Well, yeah, that's 27, and so that works as well. Now, that doesn't have anything, example 2 has nothing to do with the problem that we're working here, problem C, but I just wanted to give you a second example of when that exponent shortcut, or trick, if you want to call it that, really comes in handy. And so what does this become? This becomes log base b of 81 divided by 81. And so that's just log base b of 1. And what did we say earlier? Whenever this number is a 1, we know that the answer is 0. And so yes, we did all that work just to end up with 0, but I think this example gives us a lot of good insight into some really important properties of exponents and ways to do the work without a calculator, because you are going to have to be able to do that whenever you take your calculus class. Okay, one more numerical logarithm here. So we've got natural log of 18 minus 2 natural log of 6 plus the natural log of 4. And so the first thing that you could do here is you could move the 2 to become the exponent on the 6, which is a good idea. So let's do natural log of 18 minus the natural log of 6 to the 2nd, which I know is 36. So I'm going to go ahead and write that, plus the natural log of 4. Now, we're going to use a combination of the product and quotient rule here, using our little rule of thumb that any logarithm that's positive will go to the numerator. So 18 times 4 will go to the numerator, and since minus natural log of 36, we're going to have divided by 36. And then if we simplify that number on the inside, 18 times 4 is 72, and 72 divided by 36 is 2. If you wanted to think about it like this, 18 divided by 36 is 1/2, and 1/2 times 4 is 2. That might have been a little easier way to do it since we aren't using calculators here to do this. Okay, one more of these examples and then we'll move on to our last thing in these notes. Notice here that I've got a 2 that can go on this argument right here as the exponent, and so this will be the natural log of x to the 5th minus the natural log of x y squared. And now I'm going to use the quotient rule because of the minus sign that's in between those two logarithms. So I'm going to have x to the 5th over xy squared. And now I'm just going to simplify what is inside the parentheses. And so if I have xy quantity squared, I know that's the same thing as x squared y squared. And so now my x's will reduce. These will cancel, and they will cancel with 2 of those, so that will be x cubed in the numerator divided by y squared. Okay, last thing we want to do here in section 3.4 is talk about the change of base formula, which is helpful because the calculator only has a base 10 or a base E button, and sometimes we need to evaluate other bases. And so some of you may know about the log base button in the TI-84 calculator, and that's great and dandy, but someone had to program that into the calculator. They had to know how to do that. And so this is how you do that, by using this change of base formula here. So log base b of a is equal to either one of two things, log a over log b, and we're talking about the common log there, or natural log of a over natural log of b. And either one, whichever one you use, will give you the correct answer. It's just what you want to make sure you don't do is mix match them. You don't want to use the common log in the numerator and the natural log in the denominator. That would not be good. You want to either stick with all common logs or all natural logs. And so the argument always goes in the numerator, the base always goes in the denominator. Another way you can think about that is the bigger font goes in the numerator and the smaller font goes in the denominator. Don't think about it in terms of how big the number is. You got to think about it in terms of how big the font is. But really, probably the better way to think about it is that the argument goes in the numerator, the base goes in the denominator. So for log base 7 of 5, if I want to evaluate that using the change of base formula, this is going to be common log of the argument, which is 5, divided by the common log of the base, which is 7, and you'll be able to use a calculator to figure out what the answer to that is, and if you went to 3 decimal places, that would be 0.827. Okay, letter B, same idea. We're going to take common log of the argument, which is 8, and divide by the common log of the base, which is 0.4. And you could also, if you wanted to, use the natural log. So, if you don't believe me, you can grab your calculator, type them both in. No matter which one you do, you're going to get the same answer, negative 2.269, if you go to 3 decimal places. Okay, that's going to do it for section 3.3 and 3.4. You guys let me know if you have any questions.